Trig functions, unit circle, and the sinusoid.
Okay.
So the first one, the directions are: use the fact that the trigonomic functions are periodic to find the value of each expression. Do not use a calculator.
Okay.
The first problem is cosine of 420 degrees.
Okay. Any angle that is outside of the unit circle can be converted to inside the unit circle by subtracting multiples of 360. So if you subtract exactly one multiple of 360, you end up with the cosine of 60 degrees. Those two expressions are identical, always. All trig functions of coterminal angles are the same. What's cosine of 60 degrees?
Root 3 over 2.
No, that's cosine of 30.
One half.
Right. Let's draw that triangle just for... Those are... The cosine of 60, notice, is the same as the sine of 30.
Right.
And in fact, there is a trig identity that exists from cofunctions. Might as well cover this now. You may not have gotten to it yet, but... And of course, the reverse is also true. But notice why these are called cofunctions. Take the trig function and you stick the word CO in front of it. That's what makes something a cofunction. And they all share this property. In other words, that's why the sine of 30 is equal to the cosine of 60. And these cofunctions, have you covered those yet or not?
The cofunctions?
Uh-huh.
Yes.
Okay. Notice they're not the same as the reciprocal. In other words, the reciprocal of sine is cosecant. And the reciprocal of cosine is secant. The only one that's the same is tangent. Tangent cofunction is the same as its reciprocal. But it's the only one. I'm going to call you. Go ahead and put your thing on phone call.
Okay.
Yeah. Well, it's amazing what a difference it makes. Even with a worse quality, in other words, even with a worse audio, which it is, without having all that interference in the background, it's like amazing. So what's the next one?
Secant of 540 degrees.
All right, so what's our first step?
Finding the coterminal angle.
Okay, so what is it? There's lots of coterminal angles. In other words, you could also add 360 to that. So 900 would also be coterminal, but we're trying to get it inside the unit circle. In other words, to be somewhere between 0 and 360. So what's the equivalent?
180.
Okay. Now, that is 1 over, what's the reciprocal of secant?
1 over x.
Well, the reciprocal of the secant function is cosine.
Right.
In other words, the secant of 180 is the same as 1 over the cosine of 180. You see that?
Yeah.
And the only reason I do that is because I'm very, very comfortable working with sine, cosine, and tangent. But whenever somebody gives me secant, cosecant, or cotangent, I generally do this as my first step, because I know I can figure out cosine of 180. Since you're working with the sinusoid function now, let's figure out cosine of 180 by graphing the cosine curve.
Okay.
There's 2 pi. There's pi. There's 1. There's minus 1. What's the cosine of 180?
What qualifies as the solution?
Well, first of all, I've labeled the x-axis in radians.
Right.
So you need to convert those either in your mind or actually convert them. Let's go ahead and convert them. Now what's the cosine of 180?
0.
Now, go to the 180 mark, and where is the function? Right there. What's the cosine of 180?
Negative 1.
Okay. Which means 1 over negative 1, which is the same as just negative 1. So that is the secant of 180 also. In other words, the secant of 180 is exactly the same as 1 over the cosine of 180. With me?
Yeah.
All right.
Okay.
Okay. Now, it is usually to take, it's normal to take these angles that are outside the unit circle and subtract as many 360s as you need to get them inside the unit circle. And that's what we did here. There are some cases where if I said, what's the sine of minus 30, you wouldn't want to necessarily do that. In other words, I can turn that into the sine of 330 by adding 360, and that gets that inside the unit circle. But it's the hard way to do it with that example, because the other thing I know is that the sine of a negative angle is equal to minus the sine of the positive angle. So if I said, what's the sine of negative 30, you wouldn't necessarily want to add 360 to it to get it inside the unit circle. This would be the easier way to go. In other words, it's equal to negative sine of 30, because by now we've memorized that. That's 1/2. So the answer is negative 1/2, and that's the quickest way to get it. The quickest way to get it is not to put it into the unit circle. So sometimes negative angles, particularly fourth quadrant negative angles, are better solved by just leaving them negative and using the fact that the function is either odd or even. Remember that sine and tangent are both odd and cosine is even. All right, what else you got?
Cotangent of 17 pi over 4.
All right, when they're in radians like this, then you want to subtract as many 2 pi's as you can to get it into the unit circle. When you're dealing with an angle greater than 360, it's always correct to subtract into the unit circle. When you're dealing with an angle, a negative angle that's in the 4th quadrant, it's usually faster to just deal with it using its odd and even properties. Well, this is greater than 360 because 2 pi is 360, and this is like 4 1/4 pi. So I could even say that that's 4 1/4 pi. So how many 2 pi's can I take away?
2.
Well, that would leave it at 2 1/4 pi, which would still be outside the unit circle.
So 4.
Right. And if I take away 4 pi from 17 pi over 4, then what do I get?
Pi over 4.
So these two are equivalents.
Okay.
Okay? As opposed to when I say a 3rd quadrant angle, what is its equivalent 1st quadrant angle? Those aren't really equivalent so much. These two actually are. All 6 trig functions of this angle are going to be the same as all 6 trig functions of this angle.
Okay.
Now, what's the cotangent? Again, that's one of those secondary trig functions, so I tend to turn it into what?
Degrees.
Well, okay, that's first step, 45 degrees. Now what?
Its cosecant is x over y, so it's root 2 over 2 over root 2 over 2. So when you rationalize that, it just becomes 1.
Okay, good. I would have done this. In other words, I would have done the same thing I did on the last problem. I would have made it 1 over its reciprocal. Why? Because I know what that is all day long. That's 1. So I instantly get the 1, and I don't have to go through your... I see why you have root 2 over 2 twice, yeah. In other words, obviously the triangle they have taught you is this one here, where they've already rationalized it for sines and cosines.
Right.
Right? And so to figure the cotangent, it's really root 2 over root 2, is it not? It's, if you want to figure it directly and not do it the way I do it, then it's the adjacent over the opposite.
Okay.
Okay? The one I use that's 1, 1, root 2, same triangle. It's just this top triangle is the bottom triangle multiplied by root 2 every side. But on the bottom triangle, it comes out to be 1 a little bit easier, wouldn't you say? And it doesn't matter whether you do 1 over tangent of 45 or just cotangent of 45. Pretty easy to come up with a 1. But the secret is subtracting enough multiples of 2 pi so that we end up with an angle that's inside the unit circle.
Okay.
What else?
So this section, it says sine of theta and cosine of theta are given. Find the exact value of each of the 4 remaining trigonometric functions.
Okay, what's the sine of theta?
Negative root 5 over 5.
And what's the cosine of theta?
Negative 2 root 5 over 5.
What information do we know from those two pieces of information? Well, let me back up a second. When you have a problem like this, what's the very first step always? Sorry, I went out of order.
I'm not sure.
Draw a triangle and label theta.
Okay.
Always. That's your first step. Now label that triangle. What's the side opposite theta? Forget the negative sign. What's the side opposite root theta?
Root 5.
I meant theta. What's the hypotenuse?
5.
Okay, that's the first step, is to label as much of that triangle as you can. Now, the only meaning we're going to get from the negative sign in sine theta and the negative sign in cosine theta is going to tell us what quadrant this is in.
Right.
And what quadrant is it in? Where is sine negative and cosine negative? It's only one quadrant.
The third quadrant.
Okay. So that's the piece of information that you can do as the first step. But the most important first step is to draw the triangle and label theta and dimension 2 of its sides. What's this third side? And there's multiple ways you can do it. You can apply the Pythagorean theorem, which is the normal way. But in this particular case, they've told us what the third side is by telling us that. What's the third side? They told us cosine of theta was minus 2 root 5 over 5.
2 root 5.
Yeah. In other words, we do not have to go through the arithmetic of the Pythagorean theorem. Normally you do, because normally the second piece of information they give you merely tells you what quadrant theta is in. It doesn't actually give you another trig function value. In other words, they didn't need to tell us cosine of theta was this number. They could have just said it's in the third quadrant. And then we would have had to use the Pythagorean theorem to figure out this side. Okay. Now we have the triangle dimensioned. Now the other 4 are easy if you just read the triangle and know what quadrant you're in.
Right.
So what's the tangent of theta in this triangle?
1/2.
Positive or negative?
Negative. No, positive.
Good. What's the cotangent of theta?
Positive 2.
It's the secant of theta.
Negative 5 over 2 root 5.
Rationalize that? You have to rationalize them, is that right?
My teacher said we didn't have to.
Okay, yeah, that's the best idea I've heard in 5 years. Truly.
Yeah.
What's the cosecant of theta?
Negative 5 over root 5.
Good. And the reciprocal functions are always the same sign as their reciprocal.
Right.
You cannot have sine being negative and cosecant being positive. Okay? So
Okay.
let's back up one moment. I want to make sure you're good, because this is the easy problem where they give you the cosine, because that allows you to dimension the third side. Let's erase that and assume that they only gave us third quadrant. Now how do we get that third side? There's a fast way to get it and there's a slow way to get it.
25 minus 5, or
Good.
square root of 20, or root 20.
Good. Yeah, that's the fast way to get it, which is square root of 20, which is 2 root 5. Okay? Good.
Okay.
I tend to get ahead of myself on these and figure out the quadrant first. And the only thing I don't like about that is that this is what students have difficulty with, is making sure they do that as the first step.
Right.
And so I want to make sure you always remember the problem here is you draw the triangle and you label theta and you label two sides of it. And to label two sides of it, notice that the fact that the sign has a negative sign in front of it, I ignored that completely when I was dimensioning that triangle. The only time I took that into consideration was in determining that it had to be third quadrant, because that's the only quadrant where sine is negative and cosine is negative.
Right.
But for dimensioning the triangle, ignore that negative sign if there is one there. All right, what else you got?
So same thing, but
Okay.
sine of theta equals 2 root 2 over 3. And cosine of theta equals negative 1/3.
Tell me every step.
Draw a triangle and label theta. And
Notice theta doesn't necessarily have to be there. I could label theta as this upper one if I wanted to,
yeah,
as long as I dimension the triangle according to where I've labeled theta. That's why labeling theta is so important. Because if I happen to label theta up here, this triangle is going to have different dimensions. I mean, they'll be in different places. So how do I label the triangle now?
so the side opposite of theta is 2 root 2. The hypotenuse is 3. And the side adjacent to theta is 1. Well, negative 1, 1, which...
Well, no, it's 1. Forget the negative sign on that also for the moment. Now we're going to look at both functions and figure out what quadrant we're in.
Quadrant 2.
Okay. Now we'll be able to do all of them based on the fact that we're in quadrant 2. What's tan of theta?
Root 2. 2 root 2.
And what is its positive or minus sign?
It's negative.
Okay. It's cotangent theta?
Negative 1 over 2 root 2.
What's secant of theta?
Negative 3.
It's cosecant of theta.
3 over 2 root 2.
All right. Again, they gave you the cosine of theta, which makes the problem easier. I don't really like that. I'd rather they make you go through and solve this triangle. The only reason I think that's true is because so frequently that's what you have to do. I would say in 9 out of 10 problems that I get that are like this, they do not give you the cosine of theta. They just tell you what quadrant it's in. And usually that'll come like this. Quadrants greater than 90 degrees and less than 180. That's what they'll tell you. And that tells you that it's second quadrant.
Right.
Okay, in other words, this is the information they would give you. The sine is equal to that, and theta is between these two angles. So you would actually have had to go in and solve for this third side. And it's the square root of 9 minus the square root of 8. So it's not hard to do it. But if you don't have a lot of practice doing it, a lot of people insist upon going back to the Pythagorean theorem and saying a squared plus b squared equals c squared, and then solving that for a or b. And there's a lot of work to get to the fact that the short side is equal to the square root of the hypotenuse squared minus the other short side squared. This is what you want to memorize. Even though you can always generate it from the original Pythagorean theorem, the fact that you have to do it so frequently, you're going to save cumulatively thousands of seconds by doing it this way. Just memorizing that the short side is the square root of the hypotenuse squared minus the other short side squared. All right. What else?
So next one, same thing, but sine of theta is negative 5 over 13. And it doesn't give cosine, it just states that theta is in the third quadrant.
Okay. We'll just put a big third quadrant up there. Okay, tell me what to do.
Draw a triangle and label theta.
I should always say draw a right triangle. It does have to be a right triangle. It can't be just any triangle.
Right.
Okay.
So the side opposite from theta is negative 5. Sorry. And the hypotenuse is 13.
Okay.
So you would have to use the Pythagorean theorem?
Uh-huh.
Okay.
Unless you recognize this right triangle, there are some right triangles that you should learn to recognize, which solve you or save you even more seconds by not having to even do that minimal math.
Right.
What's the lowest perfect Pythagorean triangle?
3 by 4 by 5.
Okay, what's the second lowest? 5, 12, 13.
Oh, okay.
So the moment I see a 5 and a 13, I'm looking for the 12. Okay? Those two, the 3, 4, 5 and the 5, 12, 13, you want to recognize those also because you are forever being presented with those two triangles. And if you recognize them, then you don't have to do any math. In other words, if I gave you 12, 13, you'd know this was 5 instantly.
Okay.
What's cosine of theta?
12 over 13.
What's its plus minus sign?
Negative.
It's tangent of theta.
Positive 512.
What's its positive? Okay, good. Excuse me. Secant of theta.
Negative 13 over 12.
And cosecant of theta.
Negative 13 over 5.
Yeah. Obviously, these, I didn't do cotangent.
Oh.
It's cotangent of theta?
12 zip.
Okay. All right. Those all tend to be the same. The only difference in those problems is the information they give you to decide which quadrant you're in. That's it. And they can either give you a second trig function, like the first two problems you had, or they can tell you what quadrant theta is in, like that last problem, or they might just say the sine is this and the cosine's positive, without telling you what the cosine is. They'll just tell you whether it's plus or minus. That would also allow you to figure out the quadrant. Okay?
Okay.
What else do you want to do?
So now I've got graphing.
Okay?
It says use transformations to graph each function.
Okay?
First one is y equals 3 sine of x.
That's it?
Yes.
Okay? I like the way they put that. Use transformations. To me, that's the logical way to treat sinusoid functions. So first I'm going to draw the parent function. That's y equals sine x. Now in red, what transformation is happening?
A horizontal compression.
First of all, that number is outside the function. Agreed? It's not the sine of 3x, it's 3 times the sine of x.
Right.
So the fact that it's outside the function means it's a vertical transformation. All verticals, including reflections, are outside the function. All horizontals are inside the function. In other words, here's some horizontals. That would be horizontal. That would be horizontal. That would be horizontal. You notice what I'm saying by being inside the function?
Yes.
Okay. And here are functions that are vertical transformations. That one right there, or y equals sine x plus 4, that's outside the function. Y equal negative sine x. Notice that's outside the function, and I call it vertical because it's a reflection over the x-axis. That's a vertical reflection. Okay. All right. So that's the way to keep your transformations straight. Is always remember that if it's outside the function, it's a vertical, and if it's inside, it's a horizontal. Well, this is a vertical what? Is it a shift, a stretch, a shrink, a reflection? What is it?
Stretch.
Okay. Now what that means, if I think of this algebraically, it means that if I had a point that was right there on my original curve, it's got to be 3 times further away from the x-axis. So it's got to be up there. And the effect of that is a vertical amplification on both ends. That is y equal 3 sine x. And every point on the red curve is 3 times further away from the x-axis as the black curve.
Okay.
Okay, including on the negative side. In other words, if I look at that point right there, well, notice where the red is. 3 times further away from the x-axis. And this is a stretch because it does change the shape of the curve. Notice, it's not the same shape. It's either vertically stretched or horizontally scrunched, whatever you want to think about it, but it's definitely not the same as the black curve.
Right.
Okay. Is the next one also a sine function? If it is, I'll only erase the red.
No, it's cosine.
Okay. In which case, I'll redraw it. So this function is y equal cosine x. And what is the function they've given you?
Y equals cosine of x plus pi over 4.
And that's in parentheses?
Yeah.
Okay. So what is that plus pi over 4 going to be? What is it called? What kind of transformation is it?
Horizontal shift.
Good. Which direction?
To the left.
Good. So what that means, if I were to label this original curve, that's pi over 2, that's pi, it's 3 pi over 2, and that's 2 pi. So if I want to move pi over 4 to the left, let's see, that would be negative pi over 2. So this would be negative pi over 4. So this point right there is going to start right here. Let me mark it in red. And that's the way I'm going to do this transformation. Then I'm going to draw a normal cosine curve as if this was the y-axis. In other words, it's going to look something like this. Notice that shifts do not change the shape of the curve. My red curve should be exactly the same shape as my black curve, only it's starting pi over 4 to the left of the origin as opposed to at the origin. Or I should say this point right here is now minus pi over 4, comma 1. That red X.
Right.
Now, there's two ways to do this. The way I just showed you is kind of the way I always used to do it. Just seemed to me easier to draw the curve unshifted and then shift it. Since I knew its shape was not going to change, that's all I had to do. Well, I've since kind of discovered that there's a better way of doing it. And that's not to draw the original curve at all. Maybe when you're first working with this stuff, that's harder to do. But if I want to draw the shifted curve, well, I know the cosine curve starts at x equals 0, right?
Right.
So the shifted curve, you've already told me, is pi over 4 to the left. So I know I'm starting at that point right there. And I know my total period is 2 pi. Right? Well, if I add 2 pi to minus pi over 4, I get 7 pi over 4. So I know I have to end it right there, which is 7 pi over 4, comma 1. And now I'm going to do it this way. I'm not going to draw the original curve. I'm going to know that I've got this point as the beginning point, this point as the ending point. Let's quarter it up. Well, where am I going to go through 0? Well, where's halfway between these? In other words, not 0. I'm going to hit my -1 down here somewhere, approximately halfway. What are the coordinates on that point? What's halfway between negative pi over 4 and 7 pi over 4?
Pi comma negative 1.
To find it out, you add the 2 and divide by 2. So when you add them together, you get 6 pi over 4. Divide that by 2, you get 6 pi over 8. That's 3 pi over 4. Comma negative 1. In other words, 3 pi over 4 is halfway in between these two. Notice that it's exactly 4 pi over 4 from minus pi over 4, and it's exactly 4 pi over 4 from 7 pi over 4. Okay? So, now I still have to find my other quarter points, because I know there's a quarter point somewhere there where the cosine curve's got to go through the x-axis on its way down to its minimum. Well, what are the coordinates of this point?
Pi over 4 comma 0.
No. Add the 2, add negative pi over 4 to 3 pi over 4 and divide by 2. That's how you find the midpoint of anything.
Okay.
What do you get?
Pi over 8.
No, you get 2 pi over 8. In other words, when I add this number to this number, I get 2 pi over 4, correct?
Right.
Then I got to divide it by 2, which gives me 2 pi over 8. That's the same as pi over 4. So that point is pi over 4 comma 0.
Right.
And the only other point that matters to me is somewhere in here. And to get that, I'm going to average this coordinate with this coordinate up here. Add those two, divide by 2, what do you get?
Pi over 4.
Uh-huh.
Comma 0.
Now that I got my 5 points, it's real easy to draw a curve through those. I know it's got to go through that, it's got to go down to there, it's got to come back up through the 0, and it's got to go to there. In other words, it's still going to look like a cosine curve. It's just going to have been shifted. Now, this may not seem like an easier method to you, but trust me, it is. One of the things that you're going to constantly have to do is draw your beginning point, draw your ending point, and quarter it. And you saw what's involved in quartering it. I find the midpoint, and then I find the midpoint of that midpoint. That's how you quarter a curve. You're not always going from minus pi over 4 to 7 pi over 4 either. Sometimes you're going a total of 4 pi. In other words, if I were to give you the function y equal cosine of 1/2 x, that has a period of 4 pi. And then if I wanted to subtract, or let's do the same thing, do that. Okay, now this problem is significantly tougher because it doesn't have the same period. Let me show you how I would do this. Let me just redraw the whole thing. I didn't mean to lose that. Here, let me erase this. Want to make sure you know how to quarter it. That's one of the bigger problems there is. Okay, so we did that. Now let's do this one. First of all, there's two things going on here. What are they?
A vertical shrink.
Right?
No?
No?
And a
Yes.
horizontal shift.
Actually not. Interesting. Very interesting. With the sinusoid function, my rules don't really apply as to being inside or outside the function. That 1/2 looks like it's outside the function, doesn't it?
Yeah.
But it's not. It's inside the function. Outside the function would look like this.
Oh, right. Okay.
Okay? So that 1/2 is actually inside the function.
Right.
And the thing you really should remember is that I'm sure that at some point they've given this sinusoid function like this. Tell me if they haven't. Have you seen something that looks like this?
Yes.
Okay. Notice that b, you're always defining that b as being 2 pi over the period of the function. And the period of the normal function is 2 pi, so b would normally be 1. But in this case, and this also means the period is equal to 2 pi over b. In other words, if b is equal to 2 pi over the period, then the period is equal to 2 pi over b. So for the function that I've given you over here on the left, what is its period? Two pi over what?
2 pi over 1/2.
Which is?
4 pi.
Right. Now, I know that pi over 4 is still a phase shift of pi over 4 to the left. So here's how I'm going to plot this thing. I'm going to start by going pi over 4 to the left. Start my function at minus pi over 4. And I'm going to figure out, and if that's 1, and this is minus 1 down here, then I know I'm going to start right there at that point where I put the x. My period is 4 pi. So to get to my last point, I've got to add 4 pi to this. Well, what does that give me? That gives me 15 pi over 4, right?
Okay.
Now I got to quarter that up. Okay, I know that my midpoint is my lowest point of the cosine function. Remember what the cosine function looks like. Your midpoint is the lowest point. So what is that point on the x-axis? Add the 2, divide by 2.
7 pi over 8.
What is this midpoint? Add this one to this one, divide by 2.
Five pi over 4.
It's actually 3 pi over 8. In other words, oh, excuse me, I'm sorry, I made the mistake. Is this, hold on a second. This isn't right.
Oh yeah, no, that isn't right.
Okay, let's go back and do it. I was not thinking. When I add the two, I get 14 pi over 4 divided by 8. I get 14 pi over 8, which is 7 pi over 4. That's what that point right there is. 7 pi over 4. Now, in other words, you don't usually need to find a common denominator ever with these.
Okay.
Now find this first quarter point.
3 pi over 4.
And find the third quarter point.
11 pi over 4.
Okay, so I know the curve, let me put this in red, has to start right there, has to go through the x-axis at the first quarter point, has to hit its minimum at the second quarter point, come back through the x-axis at the third quarter point, and finish at the last quarter point. And then drawing the curve is relatively easy. But notice the period here is 4 pi. And I had to quarter up a period that was 4 pi, not 2 pi. So whenever you have a b that's other than 1, you're going to have a period that's not 2 pi. And you need to start there. In other words, you can start at the phase shift like I did, but then you have to know that that 1/2 gives you a period of 4 pi, so that allows you to figure out your first point, your last point, and to quarter it up. And trust me, this is the easiest way to do this. Not to draw the original. I mean, I suppose I could have drawn the original, but it doesn't really help that much here. The key really is to find your starting point and your ending point, and then quarter up everything in between. Okay. What else they give you? We got time for at least one more.
Yeah. So, yeah, it says graph the sinusoidal function.
Okay.
And it's y equals 4 cosine of 6x.
Okay, and over here I'm going to put the standard. Now, I better ask you, is this the standard they taught you? Because there's actually a few different standards. There's one standard where the b is inside the parentheses. And that kind of makes all the difference in the world. Doesn't affect the period, but it definitely affects the phase shift.
The way they taught it was that the equation that you will usually get initially has b distributed to the x and the c.
Okay.
And you have to
Let me write that general formula. Notice the difference. So you're saying the one they generally give you is that one?
No, it's bx minus bc.
Wow. A fourth format. Wonderful. Well, notice that if I take the second format, and you might get your function in either of these formats. Let's say I gave you something that looked like this. Or I gave you something that looked like this. Notice that this top one fits my first format. And the beauty of that is that pi over 4 is the phase shift. In other words, my preferred format is this first one,
Right.
because you immediately know what B is and you immediately know what the phase shift is. If it's given to you in the second format, you have to factor out B. In other words, I got to turn this into 2 sine. I'm going to divide everything by 3, and that leaves, I meant x, excuse me, that wasn't a pi.
Right.
And that leaves what the first one was. Same thing. It's just that in this second format here, I don't immediately know what the phase shift is. It's not 3 pi over 4. I have to factor out that B before I know what the phase shift is. So that's why I prefer this first format there, is that you immediately know what the phase shift, the amplitude, and the vertical shift is. And regardless of which format you're in, it doesn't change B. B is still always 2 pi over the period, regardless of which format it is. Okay?
Okay.
So let's look at the function you gave me. Figure out how to get my eraser working. And this function you gave me, it doesn't matter which format because there's no phase shift.
Right.
So as long as there's no phase shift, both formats tend to be the same. So A is 4, B is 6. What's the period?
It's one thing in the formula for B, shouldn't it be the period equal 2 pi over B?
That's the same thing. Algebraically manipulate that and you get that. In other words, these two are equivalent to one another. Those two right there.
Okay.
If B is equal to 2 pi over the period, then the period is equal to 2 pi over B. If you multiply both sides by period and divide both sides by B. Okay? So both of those are the same. Sometimes they give you B, but sometimes they'll show you a graph and you'll be able to figure out the period and you got to calculate B. So you use both of these equally, probably, an equal amount. Well, in this case, they gave us the formula. We got to figure out the period. So what's the period? What's the period?
Pi over 3.
Okay. Now, that's all I need to graph it. If that's 1, and that's -1, and there's no phase shift, this is a cosine function, so I'm starting at the origin. So this is one of my quarter points, and I'm going to end, well, I don't want to draw that yet because the amplitude stretches this thing up to 4 and down to -4.
Right.
Okay, so I will start with the red curve. That's my starting spot right there. What's my ending spot over there? In other words, what's that point on the x-axis?
Pi over 3.
Okay, good. Now, we got to quarter that up. What's this point? What's this point? What's this point? What's the middle point?
The middle point.
Mm-hmm.
Pi over 6.
Correct. It's this point here on the left.
Pi over 12.
And this point here, the only point left. Add pi over 6 to pi over 3, divide by 2. pi over 6 added to pi over 3, which is 2 pi over 6. In other words, I do need a common denominator here. That's 3 pi over 6 divided by 2 is 3 pi over 12. That's the same as pi over 4. So in this case, I got 4 different denominators. Not that unusual, because the total period was a fraction. It was pi over 3. Okay? Now I know how to graph it. I know my bottom point is going to be there. My crossing the x-axis point's there. My crossing the x-axis point is there. And the function graphs like that.
Okay.
So this concept of drawing your starting point and your ending point and quartering it up is virtually every problem. So get used to that process. And once you're used to that process, then it actually makes handling phase shifts the way that I suggested doing it the easier way. Because you've got to learn how to quarter these things up, no matter what their numbers are. You got to be able to add them and divide by 2. And that's as simple as it gets. Add the 2 numbers and divide by 2. That's your quarter. That's your midpoint between those 2 numbers.
Okay.
Okay. That's what you really did to get pi over 6, was you added 0 to pi over 3 and divided by 2.
Okay.
Okay. All right, William. Sounds like a good stopping point.
Yes.
And remember, on these sinusoid functions, you're going to have to go both ways as often as, in other words, they're going to give you a function, you got to graph it, and they're going to give you a graph, and you got to come up with the function.
Right.
So that's why you need to know that b equals 2 pi over the period, or the period equals 2 pi over b, depending on which it is you're trying to solve for.
Okay.
Okay. All right. You have a good week, and I will talk to you next time.
Thank you. You too.
Bye-bye.